Assalamu alaikum dear students. I welcome you to the 23rd lecture of probability and stochastic processes. In previous lectures we have been discussing the behavior of a scalar valued derived random variable. I call it derived because it assumes values which are functions of values of two other random variables. The two other random variables are basic or underlying random variables because they assume their values directly as the outcome of the random experiment. And we combine these values of underlying random variables using a function to form a new random variable which I call derived random variable. To give a better visualization, we were working with an example of two television sets and their failure times. The two television sets were assumed to be manufactured by two different manufacturers, and one of them was assumed to be more reliable and the other less reliable. The random variables modeling the service time or failure time were x and y, where x represented the service time or time before failure of first television, and random variable y was modeling the behavior of second television, the service time of second television. We learned that if we want to answer questions which involve both x and y, we can answer those questions in a better way if we form a new random variable, a derived random variable z. For example, we can say that z is x plus y, or z is the sum of service times of two televisions. So if we form this z, a derived random variable which takes its values based on the service times of first television plus the service time of second television, then this random variable z has its own probability density function and CDF or cumulative density function, and we can use these CDF and PDF to answer questions which were about z or total service time. For example, we could answer questions like this: what is the probability of having a total service time of more than 60 months? We could form other derived random variables on this pair of underlying random variables x and y. For example, we can have z equal to y minus x, or z equal to minimum of x and y, or maximum of x and y. And then we can answer questions related to the maximum of two service times, the minimum of two service times, or difference of service times of two televisions by working with appropriately defined derived random variable. Today, we'll continue with our discussion of derived random variables, and we'll extend our discussion by considering more than one derived random variables jointly, and then we'll try to answer questions which involve more than one derived random variables. When we are working with more than one derived random variables, we are going to find the joint probability density function of the two derived random variables and then work with this joint PDF to answer questions which involve more than one derived random variables. Once again, we'll find the PDF indirectly by first finding the CDF, because CDF is easy to find because CDF is a family of parameterized probability values, and when you have this collection of probability values, you can find the PDF by taking differentiation of the CDF. In case of scalar valued random variable, we simply take derivative with respect to the single parameter of the CDF. When you have a CDF of two variables, then to get PDF from the CDF, you take double partial derivative with respect to both of the parameters. To motivate the need for working with two derived random variables, you should consider how more than one random variables come into observation and how we take this type of pair of random variables to answer questions involving more than one random variables. For example, let's look at the example of two televisions and the underlying random variables X and Y. The underlying experiment is that we have two televisions made by two different manufacturers, and we observe their failure times, their service times, or the time they serve us before they fail. And there are two observations. One is for first television, other is for the second television, and we model the failure time of first television with X and failure time of second television with Y. If we have such an experiment which gives us two observations, two values, then we can answer questions related to only one random variable. For example, in case of the televisions, we can ask questions which involve only the first televisions. Questions like, what is the probability that first television give us a service time of more than 24 months or less than 6 months? Similarly, we can ask questions which involve only the second television. Questions like, what's the probability that second television will give us a service time of more than 30 months or less than 12 months, etc., etc. And it's also possible to answer questions which involve behavior of both televisions. Questions like, what is the probability that the total service time is more than 60 months or less than 12 months? Or what's the probability that the difference of two service times is between -6 months and +6 months? That is, the two televisions fail within 6 months of each other. Even the first television can fail before the other, or the other television can fail before the first one, but they fail within 6 months of each other. Such questions involve behavior of both televisions, and we learned in previous two lectures that it is better to form a derived random variable like z is equal to x plus y, or z is equal to x minus y, or y minus x, then find the PDF and CDF of this derived random variable z and answer questions directly in terms of z, which actually involve behavior of both televisions. So the behavior of two televisions is summarized in behavior of a new derived random variable z, and by finding the PDF and CDF of z and processing this PDF, we can answer questions which involve behavior of both televisions. It's not necessary to form a derived random variable to answer questions which involve behavior of both televisions. There are some questions which can be answered directly. For example, we can ask this question: what's the probability that the first television will give us a service time of more than 24 months and second television will give us a service time of more than 30 months? This question can be answered directly from the joint PDF of X and Y, or actually it can be answered by working directly with individual PDFs of X and Y. The reason is we assume that X and Y are independent of each other. When they are independent and the total event that we are interested in is two-part event, where one part is based on the behavior of random variable x, and the other part is based on behavior of random variable y. Then probability of the whole event is just multiplication of probability of first part and probability of second part. For this question, which is what's the probability that first television gives us a service time of more than 24 months and second television giving us a service time of more than 30 months, the probability of this event is simply multiplication of two things. First is probability of first television failing after 24 months, and the second is the second television failing after 30 months. So there are other questions which are easy to answer because x and y are independent of each other. But for other questions like the sum of two service times, the difference of two service times, etc., they are easier to answer if we form a derived random variable z, find its PDF, and work with the PDF of z to answer these questions directly instead of working with the joint PDF of x and y. When we are working with derived random variables, we can have more than one derived random variables and answer questions based on the PDFs of these derived random variables, which in effect are answers to questions which involve combined behavior of two underlying random variables x and y. For example, if we have x and y modeling the service times of television, then we can have more than one derived random variable on this pair of underlying random variables. First derived random variable can be u, which is defined as y minus x. So u is a new derived random variable which models the service time of the difference of two service times, the service time of y minus service time of x. If you have this derived random variable u, then you can answer questions like this. What's the probability that two television sets fail within 6 months of each other? We can have another derived random variable v, which is defined as x plus y, or sum of the two service times. If we have this derived random variable v, we can answer questions like this. What is the probability that total service time will be more than 60 months? Now let's take a big jump and ask questions which involve both u and v. A question like this: what is the probability that the two television sets will give us a total service time of more than 60 months and the two televisions will fail within 6 months of each other? So this is a complicated question which involves behavior of two televisions, but the question is not directly about the behavior of two televisions but about sum and difference. So instead of asking a question which directly relates to failure time of first television and failure time of the second television, we ask question which relates to total service time as well as the difference of the service times. Such questions can be answered in two ways. First is that you look at the question carefully and you map this question to the original xy plane where the joint probability density of x and y, the underlying random variables, is defined. And when you clearly find the region which represents the complicated question, you can find the probability of that region by integrating the joint PDF of x and y defined over the part of xy plane. Or you can find the joint PDF of u and v, the two derived random variables, and from this joint PDF you can find the probability of the event representing our question, and doing this will be based on integrating the joint PDF of u and v over appropriate region. We are going to use both of these techniques for this question that we have raised, that what is the probability of two televisions giving us a total service time of 60 months and failing within 6 months of each other. To answer this question, we need to find the joint PDF of u and v. That is the second approach I mentioned. But the question is, how do you find the joint PDF of two derived random variables? So far, we have been using the technique of finding the probability of derived random variables, one derived random variable at a time. So if we define u as y minus x and v as x plus y, then we can find the individual PDF of u and individual PDF of v. But can we combine these two to form the joint PDF of u and v? The answer is yes, provided that u and v are independent of each other. If they are, then the joint PDF of u and v is simply multiplication of individual PDFs of u and v. But we cannot be sure that the two derived random variables are independent of each other. So we usually do not assume independence, and we find the joint PDF of u and v from three things: the joint probability of x and y, the two underlying random variables; second, the function g, which combines x and y to give you new random variable u; and function h, which combines x and y to give us a new random variable v. In this example, g, the function which combines x, y to give u, is y minus x, and function h, which combines x and y to give us v, is x plus y. So we use these two functions and the underlying joint probability density function of x and y to come up with joint PDF of u and v without making any assumption of independence of u and v. Once you have found the joint probability of u and v, you can find the marginal densities of u and marginal density of v from this combined joint probability density function, and this is a definitely robust method because it does not assume any independence between u and v. Once you have these two marginal densities, you can multiply them together and see if the multiplication of two marginal densities is equal to the joint density of u and v. If they are equal, then u and v are independent, but usually they are not, and we should not make such an assumption. Hence, you first find the joint PDF, and from that joint PDF you can find marginal densities and other quantities of interest that can be used to answer complicated questions. So the first approach of answering a question which involves behavior of x and y through two derived random variables is that you look at the question carefully and find the region on xy plane which represents this event. Once you have found that region on xy plane, you can integrate the joint density of x and y over that region to find the probability of the event of interest. In this case, the event of interest is that what's the probability that two televisions will give us a total service time of more than 60 months and they will fail within 6 months of each other. Let's look at the next slide, which shows how we can use these constraints to narrow down the region of xy plane which will be used for integration and this integration will integrate the joint PDF of x and y over that region to find the probability of this event. On your screen you can see the joint PDF of x and y, and this PDF is a sloping surface with peak at origin, and as you go away from peak in the first quadrant of xy plane, the surface falls off, and this fall off is controlled by the exponential distributions representing the PDF of x and PDF of y. On this first quadrant of xy plane, you can see the partition. This partition is a diagonal line which partitions this sloping surface into two regions. The region closer to origin represents those points xy which give us a total service time of less than 60 months, and the region away from origin to the right of this 45-degree line, actually it is 135-degree line, to the right of this line, the points x comma y, the observations of two service times, represents those points which give us a service time of more than 60 months. If we were interested in just finding the probability of this event, that the total service time is more than 60 months, you will integrate the joint PDF of x and y over this region which is away from origin. This line, by the way, cuts the y-axis at 0, 60, and it cuts the x-axis at 60, 0. So all the points in the first quadrant which are away from origin, above and to the right of this line, represent this event, that the two televisions give us a total service time of 60 months. But we have another constraint, that the two televisions fail within 6 months of each other. This constraint restricts the region of integration, and this constraint is given by this equation, that y minus x, the difference of two service times, falls between -6 and 6. So difference is more than -6 but less than +6. So if you take these two equations actually to inequalities, that y minus x is greater than -6, and rearrange terms, you get an equation that y is greater than x minus 6. And if you take the other side of the constraint, that is y minus x is less than +6, and take x on the other side, you will get y is less than x plus 6. So this constraint is a narrow strip bounded from above by the line y plus 6 and bounded from below by the line y is equal to x minus 6, and it goes along the 45-degree line and it goes all the way to infinity. So this narrow strip represents those points x comma y such that x comma y form a difference y minus x which is between -6 and +6. If you combine the two constraints, then the region of interest is a narrow strip, goes all the way to infinity but does not come all the way to the origin. It stops at that 135-degree line which connects point 0, 60 on y-axis with 60, 0 on the x-axis. So from this line, diagonal line, and along that 45-degree line, there is a narrow strip which represents all the observations x, y, which give us a total service time of more than 60 months, and the two televisions will fail while giving us a service time of more than 60 months within 6 months of each other. Now it's not very difficult to find probability of this event by taking the integral over this long strip, and the integral will involve the joint PDF of x and y. So if you want to find this integral, you have to divide this narrow strip into small vertical strips, and vertical strips will go all the way to infinity. But to the left of this strip, the shape changes, so we have to divide this integral into two parts. And you can see on your screen how this integral is divided into two parts to get the complete integral. The region of integration is a long strip bounded from left by the line with equation x plus y is equal to 50, and this strip is bounded from below by the line y is equal to x minus 6, and from above by line y is equal to x plus 6. So you can take narrow vertical strips of this region, and they will be used for the double integral that is needed to find probability of that event. But if you take these vertical strip and keep on going towards this diagonal line x plus y is equal to 50, when the lower part of the vertical strip touches this line y plus x is equal to 50, to the left of that the length of the strip starts going down, because now the lower part is not bounded by this line y is equal to x minus 6, but by this line x plus y is equal to 50. And by the time you go to the upper corner, the length of this vertical strip is almost 0. So you divide this strip into two parts. One is triangle, which is bounded by a vertical line on the right, and the equation y plus x is equal to 50 from below, and the equation y is equal to x plus 6 from top. So this triangle is the first integral, and then the remaining part of this region is the second integral. And the actual values of this integral are shown on your screen, and you can see that the first integral is when you take your x, which goes from 22 to 28, and your y, which goes from 50 minus x to x plus 6. This represents the triangle. So you can take this integral, double integral, and the function to be integrated is the joint PDF. And the second integral represents the long strip, which has a form of integral where x goes from 28 to infinity and y goes from x minus 6 to x plus 6. So this constant height vertical strips are used to integrate the joint PDF, and this is the second part of the integral. If you fit in the values of the joint PDF and take appropriate terms out and make this double integral into iterated integral first with respect to y and then with respect to x, you can find that the probability under that little triangle is 0.003, and the volume of the joint PDF under that strip is 0.006. So total probability of this long strip is 0.009. So we have found the probability of this complicated event, that the two televisions will give us a total service time of more than 60 months, and they will fail within 6 months of each other. And this probability is slightly less than 1%, which is expected because we require our televisions to give us a long service time and fail in a very restricted manner. If this second restriction of failing within 6 months of each other is not placed, then there are a lot of other combination of service times which can give us a total service times of more than 60 months. But we have placed additional restriction, and we want our televisions to fail in very restricted manner, within 6 months of each other, and that reduces the probability, that reduces the region to a narrow strip which is away from origin, where the height of the PDF is very small. Hence, the probability of this complicated event is slightly less than 1%. So that was our first approach, where we looked at the question and we mapped the constraints of the question on the XY plane, where joint PDF of X and Y is defined. Once we found the region representing the event, we integrated the joint PDF of X and Y over that region to find the probability of the event of interest. Let's look at the second approach. In the second approach, we will be working with two derived random variables and we'll be working with their joint PDF. So we will be working with two derived random variables u and v. The random variable u is defined as y minus x, and random variable v is defined as x plus y. Random variable u represents the difference of two service times, and the random variable v represents sum of the two service times. And the question was, what is the probability that sum of the service times, that is v, is greater than 60, and the difference of service times u lies between -6 and 6. Suppose you have found the joint PDF of u and v, and on uv plane, where u is horizontal axis and v is vertical axis, you have your joint PDF as a surface over uv plane. Then the event on this uv plane, which represents our question, is all points u comma v such that v is greater than 60, v is vertical axis, and u is between -6 and 6. So it's a rectangular region, a long strip with lower boundary at v is equal to 6, left boundary at u is equal to -6, and right boundary at u is equal to +6. So it's a long strip starting at v is equal to 60 with width of 12 and going all the way to +∞ axis along positive v axis. So the region is quite straightforward, and if we know the joint PDF of u and v, it will be quite easy to integrate this joint PDF over this long narrow strip which is parallel to v axis and symmetric across v axis with width of just 12 units. So how do you find the joint PDF of two derived random variables u and v without making any assumption about their independence? You should recall that a joint PDF and joint CDF are related with each other through partial differentiations and integrations. So we will initially find the joint CDF, which is a parameterized family of probabilities, and the parameters are small u and small v, which are the values of random variable u and v, and the events which are parameterized by this small u and v are of the form that capital F of u comma v, which is the joint CDF of random variables u and v, is equal to probability of this event where random variable u lies from -∞ to small u and random variable v lies from -∞ to small v. So as values of small u and v increase, starting from -∞ going all the way to +∞, more and more region of uv plane is included, and this bigger and bigger region of uv plane is transformed to corresponding region of xy plane, and from that corresponding region of xy plane we can find the CDF of u and v by integrating that region by integrating the joint PDF of x and y over that corresponding region on xy plane. Let's see how we can do this for this problem. So we will find the joint CDF, which is a parameterized family of probabilities, and we'll find this parameterized family of probabilities by integrating the joint PDF of x and y over appropriate region of xy plane. So starting with the joint PDF of x and y, we look at the regions which correspond to different CDFs. Different CDF means value of CDF for different values of parameter small u and small v. So if we want to find value of CDF for certain pair of values of small u and small v, then you are trying to find the probability of this event that random variable u is less than the value of small u and random variable v is less than the value of small v. As you know, u is y minus x and v is x plus y. So there are regions on xy plane which correspond to these probabilities, and the boundaries of these regions vary as we vary u and v. For a certain value of v, when we say that v belongs to a value between minus infinity and small v, then this random variable v, which is x plus y, is less than small value of v. So the constraint is y plus x is less than small v. So if you take x to the other side, then it comes out to be y is less than minus x plus v, or y is less than v minus x. So if you pick a value of v, any value, then this constraint represents all the points on xy plane which are below this 135-degree line, which crosses y-axis at 0, v and crosses x-axis at v, 0. So as you increase v, this line goes away and away in the first quadrant, away and away from origin, and more region of xy plane is included in computation of CDF of u and v. What about the other random variable u? When you are finding the combined joint CDF of u and v, then the other constraint is that random variable u is between minus infinity and a small value of small u. This translates to y minus x less than small u, and if you take x to the other side, it comes out to be y is less than x plus u. So if you draw a line x plus u, it is a line of unit slope with varying intercept on y-axis, and all the points below this line are included in this event, which represents the joint CDF of u and v. But there are two cases. If u is a positive number, then the line crosses the y-axis at some positive value of y, because the line is y is equal to x plus u. If u is a positive number, which is the y-intercept, then it is a positive number. Then the region which represents this CDF is bounded from below by x-axis, from left by y-axis, from top left by this line y is equal to x plus u, and from the right and above by this line y is equal to minus x plus v. And if you take a negative value of u, then this line y is equal to x plus u is again a unit slope line, but its y-intercept is a negative number. So it crosses the y-axis below origin and crosses the x-axis at a point which is right of the origin. In this case, the region of integration is bounded from below by x-axis, from the left and above by this line y is equal to x plus u, where u is a negative number, and from right and above by this line y is equal to v minus x. So there are two separate expressions for the joint CDF of u and v, which are found by either integrating the joint PDF of x and y over a triangular region or a triangular region residing above a quadrilateral region. So depending upon positive or negative value of u, you will have two different shaped regions which will be used to integrate joint PDF of x and y to get a certain value of CDF of u and v. And if you take positive value of u, then the region will be different and you will use a different expression. These two expressions are shown on your slide, and these expressions are quite similar to the exponential distributions. On your screen you can see that if u is less than 0, a negative number, then the expression for the joint CDF of u and v comes out to be e raised to power minus v over 10 plus 1 over 3 times e raised to power u over 10 minus 4 over 3 times e raised to power u over 40 minus 3v over 40. So this expression is valid as an expression of joint CDF of u and v if u is a negative number. If u is a positive number, then the expression for joint CDF of u and v comes out to be, as you can see on your screen, 1 plus e raised to power minus v over 10 minus 2 over 3 times e raised to power minus u over 20 minus 4 over 3 times e raised to power u over 40 minus 3v over 40. If you carefully see on your screen, then the upper expression is for values of u which are less than 0 but greater than minus the value of v. Similarly, the lower expression is valid if u is greater than 0 but value of u is less than v. Why we are using these additional constraints? For that, you have to look at the previous slide, actually previous two slides, and see why there are additional constraints. So if you look back at the slide which showed the area of xy plane which needed to be used in the integration of joint PDF of x and y to find value of CDF, you will see that that region is a triangular region bounded from below by x-axis, from the right by the line which was a function of v. That line crossed the y-axis at 0, v, the x-axis at v, 0. So you take a value of v. Then the value of u decides the location of other line, and wherever that location of other lines is, all the points below this line and all the point from origin to that line with 135-degree slope, the common area of these two constraints is the area that is going to be used in the integration. So fix the value of v somewhere, any value. So you have fixed the value of v. The 135-degree line starts at 0, v and ends at v, 0. Now change the value of u. If you make the value of u very negative, so negative that this line crosses the x-axis at a point which is right of v, 0, then there will be no common area. For that case, the probability of this joint event of v being between 0 and the small value of v, and u being between minus infinity to that value of u, which causes the line to cross x-axis to the right of v comma 0 will be 0. So CDF for these combination of values will be 0. So as you keep increasing u, which is still a negative number, and it goes above the value minus v. V is a positive crossing point. V is positive number. Actually, v is a random variable which is x plus u, and it is always positive. So v, the small v, is fixed at a value, and if u is more than minus of this v, then the crossing point on the x-axis will be to the left of v comma 0, and there will be a small triangle which will be the common area of the constraint, and it will give us a CDF which is non-zero. So as you keep increasing u, the line keeps increasing, and then it crosses the origin where value of u is 0. Before that, values of u were negative. So when you cross the origin, the line passes through origin, you have a triangle, the biggest possible triangle, and its area will be the CDF of u being 0 and v being whatever it is. Then you keep increasing u to positive values, and if you keep increasing u in such a way that it crosses, the y crossing crosses the point 0 comma v, then the area of that triangle does not increase. It remains constant. So imagine, if u is very negative, there is no common area. If u is from minus v to 0, the common area is a triangle. If u is between 0 and v, the common area is not a triangle, but a triangle on top of a quadrilateral. And as soon as the u goes above v, the area remains fixed. It does not increase, so value of CDF does not increase. Hence, the constraints on u and v are interrelated because we have only one quadrant of xy plane where the joint PDF of xy is non-zero. If we had a joint PDF of x and y, which was defined over all quadrants of xy plane, then we would not have this kind of difficult interrelated constraints. Then the constraint of u being less than a small value of u and v being less than value of small v would have contained the whole region, and integration would have been easier to perform. But for this case, you have to be careful. If there is a common area dictated by the constraints, then you take the integral over the common area, and if there is no common area, then the value of the CDF will be 0. Now that we have found the two expressions for the CDF, the joint CDF of u and v with their own constraints which are interrelated, we can use these expressions and the constraints to sketch the joint CDF of u and v. And the next slide on your screen has this sketch. This sketch is limited to u being from minus 50 to 50 and v being from minus 10 to 100. Actually, v is always positive, so for v axis from minus 10 to 0, the CDF is 0, and it only rises when v is a positive number. Furthermore, if you look at this region, then starting from origin and going at 135 degrees, there is no CDF below this line. The CDF only starts to the right of this 135 degree line. Similarly, for the line on UV plane which has a slope of 45 degrees, there is no variation to the right of this line. The variation of CDF is only between this V-shaped region, and when the CDF reaches this 45 degree line, to the right of it, it remains constant. So this is a nice looking joint CDF of u and v, which is 0 for the lower quadrants, which is 0 to the left of 135 degrees, varies in an increasing manner from minus 135 degree line to 45 degree line and then remains constant. So as you move in the UV plane, in the first quadrant of UV plane, further away from origin, the joint CDF will try to reach its destination value of 1. With joint CDF of U and V in hand, we can simply take its partial derivative, double partial derivative with respect to U and with respect to V to find the joint PDF of U and V. I have found that and I have sketched that, and it's again a surface plot, and you can see that on your screen. The joint PDF of U and V is shaped like the joint PDF of X and Y, but there is one difference. The region over which this PDF is defined is again that wedge-shaped region starting from 45 degree and ending at 135 degree slope line. And the peak is at this point, which is origin 0, 0, and then it slopes away as we move into the first and second quadrant. Now the joint PDF is defined half of the first quadrant and half of the second quadrant. So as we move towards positive V-axis away from origin in either first or second quadrant, the PDF falls down. And interestingly, even though we had two different expressions for the joint CDF of U and V, when you take their partial derivatives, the expression for joint PDF is same, whether you take negative value of U or positive value of U, and that expression you can see on your screen is 1 over 400 times e raised to power U over 40 minus 3V over 40. So you have your joint PDF, you have your region over which it is valid. On all the points U, V which are not in this region, the PDF is 0, and you can use this nice looking PDF defined over a strange but interesting region to find probabilities of different events involving both U and V. We have run out of time, and I'm going to use this PDF to find the probability of the event of our interest, that is U is between -6 and 6 and V is more than 60 in next lecture. Till then, I wish you the best. Thank you. Khuda Hafiz.